This is a Eurocopter A-Star AS350B2. This engine here weighs about 200 pounds and develops 745 horsepower. Burns about 45 gallons of fuel an hour. It has fewer moving parts than a car engine. One part of the engine runs a compressor that compresses the air down to 20:1, heats the air up as it compresses it down that tight, to about 500 degrees, and then it's put into a burner can where it's ignited and then provides the heat that also then produces the thrust that turns the wheels, that turns the blades. This aircraft then will fly along at about 135 miles an hour or so. These things now are going for about $1.5 million for a new one. The overall construction of the helicopter is aluminum riveted together with rivets. It does have quite a bit of fiberglass components in this one. The side doors, cowling, are fiberglass. The main rotor blades are also fiberglass with a stainless steel leading edge for abrasion. And because of that, then they don't require to be replaced as often as aluminum does, because metal sits there and works back and forth and eventually fatigues and cracks, where the fiberglass gives us almost an infinite life blade, so we can get a lot more hours out of a blade, where aluminum main rotor blades are only good for about 3,000 to 5,000 hours depending on the aircraft, where these blades are good for over 20,000 hours. Well, this is a cyclic control here. This control here, when you move it, it actually will tilt the disc of the rotor in the direction that you want the helicopter to move. So you want it to move forward, you push this cyclic forward, and the helicopter now will start to move forward. Pull it back, we can hover backwards, turn left or right. Then down here on the floor, these are the torque pedals, and we use these to control the amount of pitch of the tail rotor back there. So if I push on the right pedal, the nose will swing to the right. If I push on the left pedal, the nose will swing to the left. The rest of over here is our main switches, our radios, our important engine gauges, and then engine gauges that tell us what the oil pressures are, temperatures, stuff like that. This one here is a artificial horizon, which we use if we were in the clouds. This is an airspeed indicator that lets us know how fast we're going. This is a radar altimeter, which actually sends out a radar signal and bounces back off the ground back to us so that we know exactly how high off the ground we are. This here is a indicator that we use to find out if we're on course and what our magnetic heading is. This is a very sensitive instrument that tells us if we're climbing or descending, so we can find out if we're staying in level flight, or how fast we're going up or down. And then this is another navigational radio device here that lets us know if we're following an electronic beam from a radio station. And then down here, everybody's pretty much familiar with these. This is a GPS, a global positioning satellite system that we use to navigate with most of the time anymore. Then the rest of the switches are just for like generators and fuel pumps and other stuff that we need to have to run the helicopter. And this is the sliding door on the sides where we access the patient for loading. It's got a platform where the cot mounts onto it. Then we can just pull it in and out and slide the patient on there. And the flight nurses and paramedic will ride in the back and care to them while we're flying. We're trying to provide, critical care medical people, to a patient in remote, usually remote locations, and then, get them transported to where they can get the care that they need as fast as possible. And this is, the fastest way to do it. There are some helicopters that may be a little faster and stuff and actually have more room, but, then the cost of operation gets too high, to be justified in rural areas.